Okay, class, welcome back. Today we're going to be talking about trigonometric functions and their complements. Now, of course, the main two trigonometric functions are the sine and the cosine. And there's a lot of different ways to think about this and to map it out. And so one way is just to graph the sine and the cosine functions. So here's a diagram I used in a previous lecture. And if you just took somebody and said, okay, look at this green line and look at this pink line as they're graphed out here. What do you see? And one of the striking things that you're going to see that you can almost not ignore is that they're almost the exact same functions. I mean, they both go up, they both go down, they follow the same sort of periodicity. They both every time this one goes up, this one goes down, this one seems to go up and down like at the exact same time, right? Basically, one is following the other. And so you could say, yeah, they're exactly the same, but they're just off by a little bit. One is shifted from the other. And if you look down here, the shifted by pi over 2 or 90 degrees. And that's what we're going to explore today with triangles. So we're looking at trigonometric functions and their complements. And this is, once again, just bolstering a lot of the facts that you guys already know about triangles. And so say I've got a triangle here, 90 degrees. Let's just call this one 35 degrees, something like this, right? And I've got my A, my B, and my C. And part of the reason I'm using A, B, and C as opposed to adjacent, opposite, and hypotenuse will become apparent here in just a little bit. Now, many of you guys, when I give you these problems, you automatically solve for what this angle is, right? You know this is 90 degrees. You know this is 35 degrees. And so let's just take a look at this angle theta right here. We're not really sure what it is at the moment, but we can easily calculate it. You remember that all the interior angles in a triangle are 180 degrees. So you know that 180 degrees is going to be equal to 90, that's our angle right here, plus 35, that's our angle right here, plus theta. Excellent. Now, if I subtract, or if I add 90 and 35 from, together, I get 125 plus theta. So just sort of combining like terms there. And then I can subtract 125 from both sides. And I find that the angle theta is going to be 55 degrees. Nothing to it. Now if I was to find just sort of a generic triangle, right? So in this one I gave it a very specific measure. Let's say I'm drawing a same triangle and I have no idea what the relationship is here. I've got some theta here. Let's call this phi. Right, so there's another common term, or another common symbol used for angles is phi. I've still got my 90 degrees right here. And so if I'm looking at the relationship, say I know phi and I'm looking for theta, or I know theta, I'm looking for phi, the interior angles are still going to add up to 180 degrees. So I can say 180 degrees is going to be equal to 90 degrees plus theta plus phi. And so I don't know what these are yet, or say I'm given one and not the other, but I definitely know 90. So if I'm going to try to simplify this equation, I can subtract 90 from both sides. Those cancel out. And I get 90 degrees, so I know that this angle plus this angle is equal to 90 degrees. So I've got theta plus phi is equal to 90 degrees. Now say I'm given phi, but I don't know theta. And so I can basically just subtract phi from both sides because I'm given that. And so on the left side, I get 90 degrees minus phi. And on the right side, I get theta. So theta is going to be equal to 90 degrees minus phi. And that's pretty much what we had here. So in this case, I knew phi is 35 degrees, so I plug in 90 minus 35, and that's going to be equal to 55 degrees. Now check this out, okay? So let's just remember this relationship right here. 90 minus phi is going to be equal to theta. Now, if I'm looking at my triangle once again, I'm going to switch things around a little bit here. Here I've got theta, here I've got this, I've got my A, my B, and my C. So let's explore the relationship between the sine and the cosine. So say I'm looking at the sine of phi right here. So this is opposite over the hypotenuse, which is just going to be A over C. Now the cosine of phi is going to be the adjacent over the hypotenuse, which is going to be B over C. Now let's take a look at, if I'm just going to switch, just for fun, let's switch over to this angle right here. And let's figure out what the sine and the cosine of this angle is. Now so this one, because I'm looking from here, if I'm looking for the sine of theta, right, so it's going to be opposite, and the opposite in this case is B. over the hypotenuse in this case, which is c. So sine of theta is equal to b over c. I move things down just a little bit. Now, once I know this, okay, I'm starting to see there's a relationship here. So sine of theta is b over c. The cosine of phi is b over c. Well, let's figure out what the cosine of theta is going to be. Cosine of theta is going to be the adjacent over the hypotenuse. The adjacent in this case is a with theta, right? So adjacent is going to be a and the hypotenuse is going to be c. So holy cow, I've got the sine of theta is equal to the cosine of phi, and the sine of phi is equal to cosine of theta, and the sine of theta is equal to the cosine of phi. So I've got a over c right here, a over c right here. So here I know that the sine of this is going to be equal to the cosine of this, and vice versa. I also know the sine of theta is going to be equal to the cosine of this. Now I'm doing all of this just to sort of reiterate the relationship between sines and cosines. Now, let's look at this relationship back up here. Theta is equal to 90 minus phi. This is where it starts to get a little bit cool. So I'm just going to rewrite this one. So here I've got 1, 2, Roman numerals 1 and 2. Let me just rewrite 1 right here. And instead of the cosine of theta, I know that theta is equal to 90 minus phi. I'm just going to rewrite this as the cosine instead of theta. I'm just going to substitute 90 minus phi for theta. So here I've got 90 degrees minus phi. Boom. So now I've got the sine of phi is equal to the cosine of 90 minus phi. Now, these functions are complements of one another, or they're co-functions. Okay, that's what it's called, co-functions. Sine and cosine are co-functions. And it basically just means we're doing the exact same thing that we did right here. You can see it visually. They're the same function pretty much. One is just shifted a little bit from the other. It's called co-functions. Now, 2, I can do the same thing with the sine of phi or the sine of theta right here. So instead of sine of theta, I'm going to replace theta with 90 minus phi. So I've got 90 degrees minus phi. And remember, 90 degrees is pi over 2, so you can do this in radians as well. Is going to be equal to the cosine of theta. Fantastic. Once again, we've also got co-functions going on right there. Now, how this relates is if you know the sine of something, you can easily figure out what the cosine is, or vice versa. So an example problem that I could give you would be, say I want the sine of 72 degrees. And I want you to write the co-function of this simple example right here. Well, I know the sine of 72 degrees is going to be this, right? So in this case, 72 is going to be my phi. And so I would say phi is equal to 72. I can use this equation, or just remember that the cosine of, so I'm looking for the cosine of some angle. So the sine of 72 degrees is going to be equal to the cosine of 90 minus 72 degrees. They're going to be 100% equal. So 90 minus 72 is 18, so the cosine of 18 degrees. Now let's just prove this to ourselves. Let's plug this into our calculators and see what comes out. Now, make sure your calculators are in degrees. So the sine of 72, let me readjust some things right here. So the sine of 72 degrees is going to be equal to sine of 72 degrees is going to be equal to 0.951. Make sure your calculator's in degrees. Now, if I did the cosine of 18 degrees, plug that into my calculator, I end up with the exact same answer. Hopefully you guys can see that. Let me turn the light on. You end up with 0.951. 0.951. Fantastic. These are 100% equal. It means that they're co-functions. Okay, let's go on with another example and finish it out. In this case, we're just going to do a little bit of a tougher one. We're going to do radians, and we're also going to do the cosecant. Okay, so B, part of our example, I want you to find the cofunction with the same value as the cosecant of pi over 3. Now the cosecant, don't freak out, we haven't talked about the cosecant, and we're also in radians, but just remember that 90 degrees is equal to pi over 2, okay? So, and the cosecant, just like the sine is related to the cosine, the cosecant is related to the secant. So I could say the cosecant is going to be equal to the secant of pi over 2 minus pi over 3. Now this is exactly analogous to what we did right here. The sine of 72 is equal to the cosine of 90 minus 72. This is a cosecant of pi over 3 is equal to the secant of pi over 2 minus pi over 3. Now the secant of pi over 2, or pi over 2 minus pi over 3, pi over 2 over pi over minus pi over 3 reduces down to just giving them common denominators here. In this case, the lowest common denominator is going to be 6. So we've got 3 pi divided by 6 minus, in this case, it's going to be 2 pi divided by 6. So combining the numerators, I've got 3 pi minus 2 pi. I just get the secant of pi divided by 6. Fantastic. And if I was to plug this into my calculator, once again, you'd get the exact same thing. So the answer to this problem is just simply the secant of pi over 6. Looking at those cofunctions, the relationships between the sine and the cosine. That's definitely something I'm going to drive home, and I want you guys to understand fully. And we'll tackle this more in class tomorrow. I'll see you guys then.